So this lesson, 422, if you notice, a lot of it is actually not new. We're just taking the frequency tables that we did at the beginning of the unit and merging them together with conditional probability as well as independent. So it'll be a good kind of catch-all to make sure that you understand not everything we've done in the unit, but at least the more recent stuff that wasn't on the quiz. So for number one, it says Kieran likes number puzzles and is tackling the puzzle below. The puzzle is incomplete. When it is complete, one total at the end of a row will be the sum of the numbers in that row, and each total at the end of the column will be this. So basically it's saying all your vertical columns should line up and add up, and then all of your rows as well. So if you look at this, there's a couple different places you could start. Right off the bat, I see this right here. You can start in the first column. So 10 and 10 is 20, so you need 5 more for that to total to 25. And then the next column, obviously you can't do that. The next column, you're missing an entry, but you also don't have a total. But then in the totals column, you have 30 and 34, which is 64. And then we need 36 more in order to get to 100. Now, that's all of the columns. If you go back to rows, if you look at the top row, now we have a total with 2 entries. So 10 and 12 is 22. So in order to get to 36, we need 14 more. And then same thing, 5 and 8. Well, in order to get to 30, 5 and 8 is 13. So this needs to be 17. Then you kind of run out of room with the next row because you're missing too many things. But in the bottom row, 25 and 40 is 65. In order to get to 100, you need this to be 35. So now you can go back and finish these two off. 12 and 8 is 20, so this has to be 15 in order to make that work. And then 14 and 17 is 31, so 9 more to make that work. So now if I added 10, 5, and 10, I get 25. 14, 17, and 9, I get 40. 12, 8, and 15, I get 35. Then same thing here. You could also go across the rows. 10, 14, 12 gets me 36. The sum of 5, 17, and 8 gets me 30. So it should work both ways. Okay. So we're going to use those, that two-way frequency table, two-way meaning it works vertically and horizontally, in order to answer some questions. Okay. Now, this says the two-way frequency table below shows the results of a survey of students when asked what their activity of choice was. And then it's going to ask a couple things about it. Well, if you look just at the frequency table right now, you don't have any totals, and you can't do anything without totals. So you always want to check. Sometimes they're going to be given to you. Sometimes you need to find them. In this case, we need to find them. So if we add 4, 5, and 2 together, we get 11. 8, 3, and 1, we end up with 12. 2, 6, and 9, we end up with 17. And those all add up to 40. Then do the same thing across. 4, 8, and 2 is 14. 5, 3, and 6 is also 14. 2, 1, and 9 is 12. And then double check. 14 plus 14 is 28 plus 12 is 40. So it works out. Now that we've totals, we can figure out what the question is asking. It says, consider the following events that apply to a random student who participated in the survey. So 10 means 10th grade. FT means field trips. So it says, compare the probability of a 10th grader given they liked field trips and the probability of a person who liked field trips given they're in the 10th grade. Okay, so we need to find them before we can interpret the results. So if we have the probability of a 10th grader given they like field trips, remember, this is now my sample space. Okay, I don't use the formula unless I have to. Well, I go and say how many people liked field trips. Over here, that was 12. So this 12 right here is my sample space. That goes down there. And you ask yourself, out of those 12 and those 12 only, how many are in 10th grade? Well, that's 8. So you have 8 out of 12, which is 2/3, or 66.67%. Okay. Now, if you flip it, you have the probability of a student liking a field trip given they were in 10th grade. So that's saying, like, you can think of that as I pulled somebody out of the group of students they are a 10th grader, what's now the probability, that they like field trips. So now my sample space is the 10th graders. Well, that is 14. Okay. Out of those 14 people, how many like field trips? It's still 8. Remember, your numerator shouldn't change when you're comparing the same two things, but flipping your sample space. Okay. So 8 out of 14 is 4 out of 7, would get you a percent of about 57.14. Okay. Now it says interpret the results. So again, you can pick what you want, but I usually go with whatever the bigger one is. So I'm going to say it is more likely that given the group of students who like field trips, they are in the 10th grade. Rather than if you had a group of 10th graders. So this is, I'm sorry, this is saying if I had the group of students who liked field trips, I would have a higher probability of getting a student who's also in 10th grade. Rather than if I had the student or the group of 10th graders, I would have a lower probability of picking somebody who liked field trips. Okay. Now, the other part of this says, are they independent? Okay. So independence rule says the probability of 10th graders and field trips is the probability of 10th graders, sorry, I'm going to run out of room here, times the probability of field trips. Okay, so we're seeing if they have at least a 1% leeway. So the now remember, you guys, conditional probability is the only place you mess with your sample space. When you're doing independence, you're going to be using this 40. Okay, so out of those 40, how many liked 10th or were in 10th grade and liked field trips? Well, that is your 8. So the probability of that is 8 out of 40. Then the probability of a 10th grader, that is 14 out of 40. Times the probability of a field trip is 12 out of 40. Okay, so you're going back to generic probabilities. 8 out of 40 is 20%. If you multiply these together, you get 10.5%. So there's not a 1% leeway swing there. That's way bigger than that. So that means these are dependent. So they do affect one another. So you can say, let's see, a selected student being in the 12th grade, I'm sorry, 10th grade, does affect the probability that they like field trips. Sorry about my terrible handwriting, but you guys get the point. Okay. So if you think about it, if you look back to the chart, we talked about this when we talked about independence. Look at your field trips here. I'm going to erase all this stuff that I have highlighted on here. Oops, sorry, we should probably keep the totals. So if you look here, there are 8 students that liked field trips. Well, look at the other 2. It's 3 and 1. So this is the overwhelming choice. The 10th graders, obviously out of everybody, the 10th graders preferred field trips compared to the 11th graders and 12th graders. So it makes sense that that's dependent. Okay. If the numbers are closer together, you're probably going to have more of a chance of independence. All right. So this is the same idea. Okay. A little bit more going on here, but we're just going to focus on a couple things. Okay. Again, we don't have totals. So you need to go through and add everything together. It says a cafeteria manager recorded the choices of 100 students who chose one food item and one beverage. Table shows the data. And then we're going to talk about students who like milk, burgers, and pizza. So this 34 and 24 gets me a total of 58. 26 and 16 gets me a total of 42. If you add those together, it's 100, which is good because it said they chose 100 students. 34 and 26 is 60. And 24 and 16 is 40, also good because they add up to 100. So again, we're going to do the same thing, okay? So if you guys are feeling comfortable with this and just want to listen through it, that's fine. If you're feeling really comfortable with it, obviously you can fast forward a little to the part where we do the bottom questions and review simple probability. So the probability of selecting milk given they chose a burger, this is my sample space. So the total number of students that chose a burger were 58. Okay. Out of those 58 and 58 alone, 34 chose milk. So that probability is about 58.62%. And then over here, the probability of a burger given milk. Now our sample space is the kids who liked milk, which was 60, and out of those 60, it's still the same 34 that liked milk. Well, 34 out of 60 is about 56.67%. Okay. So here, they're pretty darn close. However, if we interpret them, again, going with the model of most likely, you can go with the model of least likely. It's totally up to you. As long as it makes coherent sense. So make sure you read your answers before that, or before you turn something in. It is more likely that given the students who got a burger, that a randomly selected student chose milk. Yikes, that's horrendous handwriting, but sorry. Cool. Rather than out of the students that you know chose milk, that a randomly selected student got a burger. Okay. All right. So again, it's just really taking a look at the sample space and seeing what's more likely. Now let's talk about this. Now we're doing independent. So the probability of milk and a burger should be the probability of milk times the probability of a burger. Okay. Now, if you look at this, with the exception of iced tea and pizza, a lot of these numbers are pretty close together. I mean, they're not like too far off considering our sample space. So this really could swing either way. If it's dependent, it's going to be really close. But if it's independent, I wouldn't be surprised. So again, remember, we're doing everything out of 100 because independence is your standard sample space. So milk and a burger is 34 out of 100. The probability of milk is 60 out of 100. And the probability of burger is 58 out of 100. Okay, so obviously this is 34% down here. Then when you multiply those together, you get 34.8%. So this is independent because they're within that 1% swing. So because they're independent, that means if a selected student chose milk or ordered milk, it does not affect the chance they got a burger. Okay, now you guys, I know my sentences kind of depending are a little slightly different every single time, but there's a common theme to them. So if you're struggling with writing the sentence, find one that makes sense to you and use that model every single time. Okay. And if you're struggling with that, please come see me because that's something easy we can work on this week. All right. So now we're just going to go back to simple probability. Okay. This is all going to be based off of cards, dice, and flipping a coin. Remember, you guys, you really want to try and avoid the probability formulas if you can, because it's usually faster to not if you can. So this says you're choosing a card from a standard 52 card deck. What is the probability the card you choose is red and a queen? Okay, so we want the cards that are red and queens. Oops, sorry, I have some writing on this that we can get rid of. Okay, so I want both things happening at the same time. Okay, so if both things are happening at the same time, there are only 2 cards in the deck that are red queens. They're those 2 right here. So that means your probability of getting a card that is red and a queen is 2 out of 52 or 1 out of 26. Okay. You are choosing a card from a standard 52 card deck. What is the probability the card you choose is odd and less than 8? Okay, so again, we want both things happening. So odd and less than 8, that means I don't care about any of these because I want everything to be less than 8. So these are odd, these are odd, and these are odd. That's 12 cards total. So the probability is 12 out of 52, which reduces down to 3 out of 13, not 4 out of 13. Okay. All right, you flip a coin 3 times. All right, so you guys, now you need to think of your heads and tails. So your probability there is heads, or your sample space, excuse me. Heads, tails, heads, tails, heads, heads, tails, tails. And then tails, heads, heads, tails, heads, tails, tails, heads, heads. Nope, I already did that. Tails, heads, sorry, and then tails, tails. Okay, so this is the 8 in our sample space. So it says, what is the probability that there are 2 consecutive heads given the first flip is head? So we have conditional probability. So our sample space is anything with the first flip heads. That's this one, this one, this one, and this one. So our sample space is out of 4. And then out of just those 4, what's the probability there are 2 consecutive heads? Well, this one counts because it doesn't say exactly. This one counts, and the other 2 don't. So it's 2 out of 4, or 1/2. Okay, you always want to reduce those fractions. All right, you're rolling a pair of 6-sided dice. What is the probability that the dice are the same, or the sum is less than 5? Okay, so or means both can happen. So the dice are the same. So that's your doubles, and then the sum is less than 5. Okay, so let's take a look at this. We have our doubles. Oh, this one circled for me. So all of these count. Okay, and the other part said the probability that the sum is less than 5. So this has a sum less than 5. This has a sum less than 5. So just go through and count them up. Anything less than 5, meaning we're not including 5. Okay, I think that's it. So now, since it's or, if it has an orange dot, we're counting it. If it has a red circle, we're counting it. So no matter what it has, one or the other or both. So 1, 2, 3, 4, 5, 6, 7 for the doubles, 8, 9, 10. So our probability there is 10 out of 36 or 5 out of 18. Okay. Could you use the formula there? Completely. It'll still get you the right answer. It really doesn't matter how you look at it. For number 8, you are choosing a card from a standard 52 card deck. What is the probability that a face card is also a spade? Okay, you guys, this is conditional probability because it says, what is the probability that a face card? So it's telling you you're looking at the face cards. There's 12 of them. Okay. What is the probability that if you know it's a face card, it's also a spade? 3 of those face cards are spades. So it's 1 out of 4. Okay. So remember we said also is a key word with conditional. All right, last one. You're rolling a pair of 6-sided dice. What is the probability that the sum is even and the product is odd. Okay. So we need both to be happening at the same time, the sum being even and the product being odd. Let's clear all this out here. Oh. All right, so the ones that have an even sum are here, here. So just go through, figure out all your even sums. Take your time with it. You don't want to go too fast and skip something. All right, so we have all those even sums. Now, the other part of it was the product had to be odd. So our product is odd here, here, and here. None of these products are odd. Our product is odd here, here, and here. None of those products are odd. Our product is odd here, here, and here. So it's 9 out of 36 that have the overlap. So your probability is 9 out of 36, or 1/4. Okay? So little conditional, little independence, little simple probability. Make sure you feel good about all of that. If you have any questions, please do not hesitate to ask.